And here, this is the example we have done yesterday. We see that if we're given the parabola of this equation, x squared here, then the point Q change, the line connecting P and Q is the secant line that cut the given curve here. Okay, it cut a curve at 2 points, then that is a secant line. And when Q comes closer and closer to P, the secant line here will approach to the tangent line, the red line here. Okay. Similarly, here when Q comes closer and closer, then the line will approach here. Yeah. And this is the case when Q is on the left side of P, the secant line will behave like this. Okay, anyway. Today, we will talk about velocity. Now, imagine if you are walking or driving from LSU to where? Where do you want to go? Walmart, okay. And it takes you about, and the distance of this is, suppose it is 40 miles, okay? It's a long distance. And it takes you 1 hour, right? We don't care how fast you drive, but you start from here and finish there. It takes you 1 hour, right? So what is the velocity of your driving? Yeah, will be delta S, the distance, over delta T. In this case, the distance from LSU to Walmart will be 40, and the times is 1 hour. Therefore, it is 40 miles per hour. Right, the unit. This is a fraction, that is why we write it mile per hour. It's easy. And we, yes. Very good, it's a good point. This is the average velocity, right? How about, and we don't know, sometimes we drive fast and slow, but for example, you're running from here to the door, right? It takes you only 2 seconds. When the times is very small, it's the instant velocity. We call it another concept. Okay? And the velocity is simply the change of distance over change in time. Hope you can read it. Okay. Now, let us take a look at the models here. So it is proven. If we drop something with for example, you drop something from the CN Tower in Toronto, the height of that will be 450 meters above the ground. And find the velocity of the ball after 5 seconds. Okay, this is the problem. And we accept the fact that it is given by the formula here. The distance, the function of time will be 4.9 t squared, where t is time. Okay. So let us model this problem. So the object is right here. Suppose this is the ground, right? And the object here is dropped from the sky here, and the distance here will be 450 meters. Okay. They ask us the velocity of this ball after 5 seconds. It means that after 5 seconds, the object will be somewhere, could be somewhere here. Suppose it is here, right? And if we call the vertical axis is the distance, the S coordinate, okay? Then after t time, suppose it is somewhere here. And the question is, what is the velocity when t is equal to 5? Okay. Now, remember, the velocity is the change of distance over the time. So now suppose we are given the formula here. What is S at t is equal to 5? We know that ST is 4.9 t squared, right? Use your own computer and let me know what is. Oh, good. Again, please. Good job. Wow. How about everybody? Do you get a similar same result? We're good? Nice. So how about S of 6? What is it? Again, please. Sorry, 100 and? Very good. According to the formula here, right? The time t is 6, then we have this one. So now the velocity from t is equal to 5 to t equal to 6, right? What is it? We use the same things, phenomena. V, let us call from the delta t is equal to 5 to 6 here. Then velocity of this will be, what is it? The change in distance, right? It is seem to be you're doing a good job here, and it is 6 minus 5, right? The distance at the time t is equal to 6, subtract the distance at the times t is equal to 5, and we found it here. So it will be 125, 22.5 minus 1. Oh, the other way around. My bad. And what do you get? Very good. 53.9. Good job. So this is the velocity from the times interval from 5 to 6. But now, yes. Oh, I use this sign. I mean, this means approximately. Yeah, it's not an exact number. It's a very good question. Thank you. This means approximately, not exactly that number. Okay, we round up to 1 decimal. So how about let us compute another velocity if we consider the delta t, the interval, the time interval. It's not delta t here. From 5 to 5.1. Yeah, try to do it yourself, and we will compare the result. Okay. I'm so sorry. That one is too loud. I can't hear you. Oh, I'm sorry. Thank you. This is notation in math. This means t belongs to this interval. T is in decimal. Or you can write it down from t from 5 to 6, the interval. Let us write it that way. That this is belong or okay. Then what do you get here? The velocity of this? 49.49. Very good. How about others? Same result? The unit? Yes. So it's a good question as well. Here we're using times is second, right? And the distance is meter. Then the unit should be meter per second. Good question. Okay. Very good. And then when we do more, okay, when we take the times closer and closer, it will approach to this number, 49.0049, for example, if t belongs this, from 5 to 5.001, when the times intervals, we choose it very small, then we call it the instant velocity. Okay. Are we good? Here? Or scroll up? Sorry. This is 2 examples. Yeah. Do you have any other question? Sorry? The answer of this is 49.49 here for the second part here. The second part. Okay. And here, when this table shows the different values when we pick the different times interval. When t From 5 to 5.05, the velocity will be this number. And when the time's closer to t is equal to 5, we call it the instantaneous velocity. Just a new concept. Okay, that's it. So today lectures, I think that's it for the velocity. And let us move to the section 2.2. Okay, we'll talk about the concept of a limit of a function.